Thank you, Jotong and Shuming. With this, we'll move to our last set of Spotlight talks. We'll have 4 Spotlight talks, starting with Richard Shin. Is Richard Shin here? Okay. Okay. Ilya Polusukin will actually present this talk, and the title is Improving Neural Program Synthesis with Inferred Execution Traces.
Hi, everybody. It's a joint work with Richard Shin and Don Song from Berkeley. So deep learning has becoming more and more popular to be used in program synthesis, specifically from input and output examples. And kind of a general trend is in research is to use inductive bias to improve how models learn. In program synthesis in general, it seems like execution traces of the program would be very useful for pretty much improving how models learn. Specifically, program traces provide way more richer context for your program synthesis problems. It definitely has more context on than input-output examples. They provide you with much richer kind of information about what's happening with the state machine, and it provides you context on how the state changes from elementary operations. So in this work, we're exploring a question: can we, instead of using explicit execution traces, which is hard to get from users, can infer execution traces from input-output examples and use this inferred execution traces to produce final programs. And on Carol domain, we find that this is true, and we receive state-of-the-art results both on simple and complex programs. And our hypothesis is that execution traces are providing a rich inductive bias for program synthesis problem. So the Carol domain pretty much is a programming language that is used to teach students programming in Stanford. It's a simple grid world with an agent that interacts with it. It has basic actions, some conditionals, for loops, and if statements. And the summary of our approach is a pipeline of 2 models. The first model takes input-output examples individually and produces traces for them. And the second model takes all of these traces together and tries to find a program that satisfies all of them. So diving deeper, the first model is input-output to trace. It's a pretty much convolutional model that encodes grid worlds of the input-output pair and uses LSTM to produce individual steps on a state. And we feed the actual state that you would achieve if you run the steps into the sequence model, providing a lot more context on how the state machine changes. The second model is trace to code, which now takes all of these traces from previous model and uses bidirectional LSTM to encode them. We still feed input-outputs as well, and we use LSTM to decode it, which uses attention to pick up relevant information from execution traces. So this work is following on Bunnell et al., which released a dataset, Carol dataset, with 1.1 million examples and 2,500 test examples. And each example contains a ground truth program and 6 input-output pairs. So the way we train this model is by taking all of the training examples by pretty much 6 input-output examples, training input-output to trace model, and then running it on the training data to produce inferred traces. And then trace to code model is trained on inferred traces, because if it's trained on gold traces, it actually performs worse, as it doesn't learn how to accustom for the errors in the previous model. And of course, for test purposes, we only give 5 input-output pairs, and we test on the 6th one. So here's a summary of our results. Specifically, we outperform across all metrics previous work. And the metrics we used, first of all, is exact match, which is exact token-by-token match with a gold program. It's a little bit confusing because there's a lot of possible programs that satisfy the input-outputs. So there's a more general metric, which is generalization, that evaluates how well it generalizes to the 6 input-output example. There's also top 50, which is a beam search across all the programs. And we added a new metric, which is a guided search, which allows to pretty much use 5 given input-output examples to find the correct program, and then test on the 6th one. And we also evaluate on different slices of data, showing that we outperform specifically on longer programs and more complex programs, which shows better generalization. Please stop by our poster at 31, and thank you.